The goal of this example is to determine the design wind loads associated with an interstate billboard sign that is 50 feet wide by 20 feet high and is mounted on two 16-foot diameter steel post supports. The top of the billboard is 80 feet above the ground level, and the sign is located in rural Nebraska on a flat and open site. We'll be using the wind load provisions in the 2022 edition of the ASCE 7 standard for this example. I would also be remiss if I didn't mention that this example originally comes from a textbook by Narendra Talley. The Talley textbook is a good one, however it is more than 20 years out of date at this point, having been published in 2003. In this video, I have updated the example as it appears in the Talley textbook so that it is consistent with the 2022 edition of the ASCE 7 standard. I have broken this example into 4 parts, each with its own separate video. Part A addresses the general wind load criteria. Part B addresses the force coefficients and wind forces. Part C addresses the wind loads acting on the posts. And in Part D, we'll examine the effects of an alternate topography. In this video covering Part A, we address the general wind load criteria, which includes determining the base wind velocity, determining the wind load parameters, and then calculating the design velocity pressure. The wind load provisions in ASCE 722 are extensive and are found in chapters 26 through 32 of the standard. Most of the general requirements for wind are found in chapter 26, and the 2 primary methods for determining wind loads on buildings, the directional procedure and the envelope procedure, are found in chapters 27 and 28 respectively. The main wind force resisting system is defined as an assemblage of structural elements assigned to provide support and stability for the overall building and other structure. In a building, the main wind force resisting systems are often brace frames, moment resisting frames, or shear walls. In our billboard example, the main wind force resisting system is composed of the 2 round posts that carry the wind loads to the ground through flexure. Chapter 29 is where we find the provisions for wind loads on appurtenances and other structures. And if you're like me, you might not know what an appurtenance is if this is your first time seeing the word. An appurtenance is basically something that is attached to the main structure that, within this context, is going to collect wind loads and transfer them to the main wind force resisting system. Common examples of appurtenances include mechanical equipment, signs, solar panels, etc. Chapter 30 contains provisions for wind loads on components and cladding. Chapter 31 addresses procedures for wind tunnel testing, and Chapter 32 addresses tornado loads. Chapter 29 of the provisions is most directly applicable to our current problem in that our billboard structure is classified as an other structure. For those of you who are interested, the procedure in Chapter 29 for appurtenances and other structures is quite similar to the directional procedure for buildings in Chapter 27, which makes this billboard example a good starting point for learning wind loads as they're applied to buildings. There is a flowchart in Chapter 26, Figure 26.1-1, that outlines the process for determining wind loads. This flowchart is quite useful for engineers who are new to the wind load provisions in ASCE 7. As you can see on the flowchart shown in this slide, the determination of wind loads typically starts in Chapter 26, regardless of the type of structure being considered. MWFRS refers to the main wind force resisting system, and C&C refers to the components and cladding. For our example, we are interested in how the wind loads affect the post supports of the billboard, which are considered to be the main wind force resisting system of the billboard. And since this isn't a building type structure, it falls under Chapter 29 as an other structure. One of the first things that you would find in Chapter 29 is Table 29.1-1, which is a step-by-step list of instructions for determining the wind loads on the main wind force resisting system for other structures. Those steps are not very easy to read here, so I have enlarged them on the next 2 slides. The first step of that procedure is to determine the risk category for the structure. We'll refer to Chapter 1 of ASCE 7 for guidance on assigning a risk category. The second step is to determine the basic wind speed. This is generally accomplished by using maps that are included in the ASCE 7 standard or by using online resources that are readily available. The third step is to determine the wind load parameters. There are several of these parameters that are intended to capture various effects. We'll discuss each of these when we get to them in the example. The fourth step is to determine the velocity pressure coefficient, which is a variable that is used to account for how wind speed changes based on the height above the ground and the roughness of the surrounding terrain. The velocity pressure coefficient is often presented in two ways, as k sub z or as k sub h. When it is presented as k sub z, the velocity pressure coefficient is evaluated at some arbitrary height z above the ground, and when it is presented as k sub h, it is evaluated at the mean roof height h, which is also measured relative to the ground level. The fifth step is to calculate the velocity pressure based on the wind speed and other coefficients. The velocity pressure represents the dynamic pressure exerted by the wind before it hits a specific surface, and it can be thought of as the raw power of the wind at a specific height z above the ground. Step number 6 is to determine the force coefficients C sub F for the structure. These force coefficients account for the effects of the aerodynamics of the structure and the way that the wind interacts with the structure, providing a means of calculating wind forces as a function of the dynamic wind pressure. I use the word coefficients in the plural here because there are often several cases to be considered for the wind force coefficients. The cases are different than the load combinations. These cases refer to different wind loading patterns that are required because the wind doesn't always blow perfectly straight at the face of a sign or a building, and because it rarely exerts a uniform pressure against the sign or the building. Thus, the code often requires us to consider multiple scenarios of wind loading. We'll discuss this in more detail later. The last step is to calculate the actual wind forces themselves. The wind forces are a function of the velocity pressure Q and the force coefficient C sub F, but are also dependent on the directionality factor K sub D and a gust factor G, and the area against which the velocity pressure acts, A sub S, the gross area of a sign, or A sub F, the projected area of a structure normal to the wind in other cases. One thing to note here is that for solid signs, the wind force is based on the velocity pressure at the top of the sign, Q sub H. But for other structures, such as chimneys, tanks, and truss towers, the wind force is based on the velocity pressure Q sub Z that varies over the height of the structure. To summarize, the end goal is to evaluate this equation for the force acting on the sign, where Q is the velocity pressure introduced on the previous slide. However, there is a bit of a disconnect in that the first equation calls for Q sub H and the second equation provides Q sub Z. The solution is simple, however. Q sub H is simply the value of Q sub Z that results when the velocity pressure is evaluated at the elevation above the ground level, where Z is equal to H. In order to accomplish this, the velocity pressure coefficient K sub Z must also be evaluated at the elevation Z equal to H. Thus, in that case, K sub Z is equal to K sub H. The constant of 0.00256 in the velocity pressure equation is based on Bernoulli's equation for fluid dynamics and is based on the density of air at sea level at a temperature of 59 degrees Fahrenheit and includes a factor to convert wind speed in units of miles per hour to feet per second. As a result, this equation yields the velocity pressure in units of pounds per square foot. If you prefer to work in SI units, then a constant of 0.613 should be used instead, and the wind speed should be entered in units of meters per second, and the resulting velocity pressure is in units of newtons per meter squared. In any case, the velocity pressure Q is a function of the square of the wind speed V. Thus, when the wind speed is doubled, the pressure is increased by a factor of 4. That is an important consideration to keep in mind when designing for wind. One way to find the basic wind speed is to use maps that are included in the ASCE 7 standard. There are 4 sets of maps that are included in the standard for the United States, one for each of the 4 different risk categories that can be assigned to a structure. So it follows then that the first step is for us to assign a risk category to our structure, and we do that by referring to Table 1.5-1 in Chapter 1 of ASCE 7-22. Looking through the descriptions of the 4 uses or occupancies that are listed in that table, I think that we can all agree that a failure of this billboard in rural Nebraska would represent a rather low risk to human life. Thus, we will assign it a risk category 1. With that, we can focus on the first set of mapped wind speeds in ASCE 7. Those are the wind speeds that are mapped for risk category 1 structures with a mean recurrence interval of 300 years or a 15% probability of exceedance in a 50-year period. Since we aren't given any more specific information about the location of the sign other than rural Nebraska, we'll simply choose the highest wind speed in the entire state for our design. Zooming in on Nebraska, we can see that the highest wind speed in the state for a risk category 1 structure is 107 miles per hour at a location along the northern border of the state, along the border with South Dakota. Another option that is available to us, instead of using the rather imprecise maps that are printed in the ASCE 7 standard, is to use the online ASCE Hazards Tool that is available to us free of charge at ascehazardtool.org. I happen to know that the location in Nebraska where the mapped wind speeds are the highest is in Cuyapaha County near the border between Tripp County and Gregory County, South Dakota. The coordinates of that location are 42.9978 degrees north latitude by 99.5342 degrees west longitude. If we enter those coordinates into the ASCE Hazards tool and then zoom out a bit, and then indicate that our billboard is a risk category 1 structure and that we are interested in wind load data, we can then see that the basic wind speed is 107 miles per hour for that location. With that, we have our basic wind speed of V equals 107 miles per hour. Next, we'll consider the ground elevation factor K sub E. This is a factor that accounts for changes in air density at higher elevations. Recall that the factor of 0.00256 was derived based on the density of air at sea level. As we move to higher elevations above sea level, the air gets thinner and less dense, and thus wind moving at the same speed will exert a lower pressure on a structure than it would at a lower elevation where the air is denser. To account for this, Table 26.9-1 in ASCE 7 provides a reduction factor that can be applied for structures at higher elevations. If we were to consult a topographic map, we would find that Nebraska ranges from 840 feet to 5,400 feet in elevation above sea level. So, since we don't know the elevation of the specific site of our billboard in this example, we will conservatively take K sub E as 1.0. One thing to keep in mind is that when we're looking up the elevation factor, we use the elevation of the site relative to sea level, which is different than most of the other cases where the elevation Z is taken relative to the ground level. K sub ZT is a topographic factor, and it accounts for a phenomenon known as wind speed-up that occurs when the wind is forced over hills, ridges, or escarpments. I won't go into too much detail here, but the factor K sub ZT is taken as 1.0 for the case of a structure constructed on a flat and open area without any hills, ridges, or escarpments. The last step before calculating the velocity pressure is to determine the velocity pressure coefficient. The first part of this step is to recognize that the site can best be categorized as exposure C. There is some judgment required in making this determination, but a figure from the commentary to ASCE 7 is helpful in this case. So without going into too much detail in this example, we'll categorize a site as exposure C. We will also need to know that the top of the sign is at an elevation h above the ground level of Z equals 80 feet. With that, we can determine K sub Z or K sub H by referring to Table 26.10-1, shown here. With an exposure C, we can select coefficients from this column and at an elevation of z equals 80 feet above ground level, we can select from this row. So for this case, k sub z equals 1.21. Generally speaking, this coefficient is written as k sub z, but in this case, since we are evaluating the coefficient at the top of the billboard at an elevation z equals h, k sub z becomes k sub h. With that, we can calculate the velocity pressure at the top of the billboard, Q sub h, and find that it is equal to 35.46 pounds per square foot. To summarize what we've accomplished so far, we've determined that the base wind velocity for our billboard, a risk category 1 structure, is 107 miles per hour. We have further determined that we will conservatively use an elevation factor, k sub e, equal to 1.0. Next, we determined that for a flat, open site, that the topographic factor, k sub zt, should also be equal to 1.0. Then, for a sign with a height of 80 feet, with an exposure condition C, we determined that the velocity pressure coefficient, k sub z, was equal to 1.21. Since this was the velocity pressure coefficient for the top of the sign, it is also equal to k sub h. Finally, we calculated the velocity pressure at the top of the billboard and found that to be 35.46 pounds per square foot. Recall that the velocity pressure represents the dynamic pressure exerted by the wind before it hits a specific surface, and it can be thought of as the raw power of the wind at a specific height z above the ground. That brings us to the end of Part A of this example, but there is still work to be done. In Part B, we will calculate the force coefficients and wind forces associated with the 3 wind cases that are required to be considered. Later, in Part C, we will address the wind loads acting directly on the posts, and in Part D, we will examine the effects of an alternate topography.